Right now, in the middle of a heat wave, there's a building sitting in direct sunlight that is colder than the air around it. No air conditioner is running inside it. No power is being drawn to cool it. It is not shaded, not underground, not wrapped in any machine. It is simply coated with a material that solves a problem engineers spent decades trying to overcome. Somehow, even under the midday sun, it sheds heat into the sky faster than sunlight can warm it. For as long as humans have tried to stay cool, the rule has been the same. Cold costs energy. To make a space cooler than its surroundings, you have to run a machine, burn power, and move heat somewhere else. That simple rule shaped how every modern building keeps itself cool. But as temperatures keep rising, that approach is becoming harder and harder to sustain. Today, cooling already consumes around 1/10 of the world's electricity, and demand is rising faster than almost any other major use of energy. The hotter the planet gets, the more we cool our buildings, and the more we cool them, the more electricity we consume. It is a loop that feeds itself. That raised a question a group of Japanese engineers refused to let go of. What if a surface could cool itself without drawing a single watt? Not during the cool of the night, but under the strongest sunlight, where engineers had spent decades searching for an answer. The answer to that question is remarkable. But to see why it matters, you have to start with how fast the problem is growing. 10 new air conditioners. That is how many the world installs every second. And on current trends, it will hold that pace for the next 30 years. For most of human history, people stayed cool by working with heat instead of fighting it, using thick walls, deep shade, cross breezes, water, and stone. Then air conditioning arrived, and within a single lifetime, the world switched to solving heat by burning power. It worked so well, we stopped counting the cost. That cost is now coming due. As incomes rise and the planet warms, air conditioning has become one of the fastest growing uses of electricity on Earth. The International Energy Agency has counted around 1.6 billion units in use and expects that number to reach 5.6 billion by 2050. Already, cooling consumes close to 1/10 of the world's electricity, and the energy needed to power it is expected to triple over the same period. Most of that growth is coming from the hottest, fastest growing parts of the world, where millions of families are only now able to afford cooling for the first time. As temperatures climb, that demand isn't slowing. It's barely started. Then there's the trap underneath it all. The hotter it gets, the more we cool. The more we cool, the more electricity we burn, much of it still from fossil fuels. And that burning warms the planet further, which makes us cool even more. Cooling is one of the few technologies that deepens the very problem it exists to solve. Cities make the cycle even worse. Concrete and asphalt absorb heat throughout the day, then release it long after sunset, trapping warmth in the streets and forcing buildings to keep their air conditioners running even harder, which exposes the real problem. We are trying to cool a hotter world with a solution that makes the problem worse. Every gain in comfort demands more energy, more emissions, and eventually more heat. That isn't a cycle you can optimize forever. At some point, you have to stop asking how to build a better air conditioner and start asking whether you can cool a building without one. It turns out you can. And we've known how for thousands of years. Long before electricity, people in Persia and northern India made ice in the desert on nights when the air never dropped near freezing. They left shallow trays of water beneath a clear night sky, and by morning, a thin layer of ice had formed on the surface. No machines, no hidden source of cold. So where did that ice come from? The answer is that the heat escaped upward. Everything around us, the ground, your body, a tray of water, quietly gives off invisible infrared radiation. Most of the time, the atmosphere catches much of that heat and sends it back. But on a clear night, some of it slips through and continues its journey into space. And this is the key. The atmosphere has something scientists call an atmospheric window. Within a narrow band of infrared light, between about 8 and 13 micrometers, heat can pass through the atmosphere with surprisingly little resistance. Heat, leaving at those wavelengths, can escape into deep space, where temperatures are close to absolute zero, around minus 270 degrees Celsius. In other words, every surface beneath a clear sky has a direct path to one of the coldest places in the universe. So if it's free and centuries old, why isn't every building using it? Scientists asked the same thing and kept hitting one wall. It only worked in the dark. At night, a surface can lose more heat than it gains, allowing it to cool below the surrounding air. But daylight changes the equation. Sunlight delivers roughly 1,000 watts of energy to every square meter, while the sky can carry away only about 100. Absorb even a little sunlight and the cooling disappears. To work in broad daylight, one material had to do two seemingly impossible things at once: reflect almost all incoming sunlight like a perfect mirror, while releasing its own heat like a perfect black body. For decades, no material could do both. So one of humanity's oldest cooling tricks remained trapped in the night, working beautifully, but only when the world needed it least. So the race was on to drag that nighttime magic into the daylight. On paper, the fix sounded easy. Build a surface that throws the sun away while still radiating its own heat to the sky. Simple in theory, nearly impossible to build. The first instinct was the obvious one: paint it white. White reflects sunlight, so a bright enough coating should stay cool. But ordinary white paint fools the eye, not the physics. It reflects the visible light your eyes can see, while quietly absorbing the ultraviolet and near-infrared energy hidden inside sunlight. Absorb even a sliver of that, and the sun wins. The paint heats up like everything else. For decades, that was the engineering wall no one could get past. Then, around 2014, researchers finally broke through, not with paint, but with materials engineered at the scale of light itself. By stacking impossibly thin layers, each engineered to interact with a specific wavelength of light, they created surfaces that reflected almost all sunlight while sending their own heat straight through the atmospheric window. Under direct midday sun, they cooled below the surrounding air. For the first time, the impossible had become real. There was just one problem. It only worked in a laboratory. These were delicate structures, grown layer by layer in vacuum chambers, using the same costly process that makes computer chips. It was beautiful science, but it wasn't something you could build at the scale of a city. You can't manufacture that by the acre. You can't wrap a skyscraper in a microchip. That was the real engineering challenge. Physics was no longer the barrier. The challenge was turning it into something affordable, durable enough to survive years on a rooftop, and practical enough to manufacture for entire buildings. For nearly a decade, that gap held, until a company in Japan set out to close it. That company is SpaceCool, a venture born out of Osaka Gas, one of Japan's industrial giants. And what they built wasn't a better lab experiment. It was a material you can unroll. Instead of a fragile structure grown in a vacuum chamber, SpaceCool made a thin, flexible film. one you can produce in sheets and fix onto a rooftop, a wall, a truck, a water tank. The same physics the lab had already proven finally turned into something you could actually manufacture, ship, and install. And here's how it works, and the trick that had looked impossible. The material does two opposite jobs at the same instant. Picture a two-way filter. One side is a near-perfect mirror, throwing back almost all the sunlight that hits it. The other acts like a chimney, carrying the surface's own heat through the atmospheric window and out into space. Mirror and chimney built into a single sheet. Together, they allow the surface beneath it to stay cooler than the surrounding air, even under the midday sun, without drawing a single watt of electricity. But that physics wasn't the real breakthrough. The lab had already proven it years earlier. What SpaceCool cracked was the harder problem, making it cheap and making it survive. Their film is built to take years of sun, rain, and grime on an exposed rooftop, 10 to 15 years of it, and to be produced at the scale of buildings, not microchips. That was the breakthrough, not discovering new physics, but turning it into something the real world could actually use, which raised the only question that actually matters. A material can be brilliant on paper, flawless in a factory, and still fail the moment you bolt it to a real building in a real heat wave. So what happens when you put it where it actually matters? Out there, under the sun, on real rooftops, through real summers. Does it still hold? It holds. And you don't have to take the lab's word for it. You can look at the buildings already wearing it. At the 2025 World Expo in Osaka, the Osaka Gas Pavilion shimmered under a silver skin. SpaceCool's film across its exterior, shedding heat while crowds moved through the summer outside. But the real test wasn't the showcase. It was the ordinary rooftops. In Saudi Arabia, where summer can turn portable site cabins into ovens, the film was installed over prefabricated housing. And the project reported cooling energy dropping by as much as 40%. In Abu Dhabi, a tennis court at the Emirates Palace was covered with a SpaceCool membrane, allowing matches to continue through the day's heat with far less air conditioning. The measured numbers are where it turns convincing. Across its field deployments, SpaceCool reports 3 different results: exterior surfaces running below the surrounding air, indoor temperatures falling by as much as 10 degrees Celsius, and cooling energy reduced by roughly 30 to 40%. Keep those 3 apart. They're different claims: a cooler surface, a cooler room, and a smaller power bill, each measured its own way. And it isn't limited to one climate. Today, the film is already protecting rooftops, warehouses, vehicles, and water tanks across Japan, Thailand, and the Gulf, some of the hottest places on Earth, where every degree of cooling matters. Which sounds like the end of the story: a free, passive layer that cools almost anything, almost anywhere. So why isn't it covering every roof on Earth? Because for everything it can do, there are still things it can't. And understanding those limits is the difference between treating it like a miracle and using it like an engineer. So where does it fail? Because everything real has a limit. And a technology is only trustworthy once you know exactly where its edges are. Start with the sky, because the sky is the whole trick. SpaceCool works by sending heat through that atmospheric window. The clearer and drier the air, the more effectively that heat can escape. On a bright day in the desert, it's spectacular. Under thick clouds or heavy humidity, that window narrows and the cooling softens. It doesn't stop working, but a rooftop in humid, rain-soaked air won't perform the same way as one under the clear skies of Riyadh. Physics has good days and bad days, just like the weather. Then there's a question every builder asks: cost. The film isn't ordinary paint, and it doesn't carry an ordinary price. Covering a large roof requires a significant upfront investment, and for many builders, that's the hardest part of the decision. But look at where it lands over time. No wiring, no motor, no electricity, nothing to switch on. It keeps reducing heat every sunny day for years without consuming electricity. The cost is a wall at the start and a saving every day after. And the longer it sits on the roof, the more sense it makes. And the hardest limit is the one people most want to ignore. This does not replace your air conditioner. On the worst day of the year, in a packed room, you will still reach for the machine. And SpaceCool cannot take its place. But that was never the job. Think of it as reducing the workload. It lowers the heat your building fights before the air conditioner ever switches on, so the machine runs less, burns less, and lasts longer. It's not the hero that defeats the heat. It's the quiet partner that makes the hero work less. And that reframes everything. Because a technology doesn't have to replace the old world to change it. Sometimes it just has to carry part of the load. Which raises the bigger question: if a thin sheet of material can quietly reduce the world's need for cooling, where else could this idea change the way we build? Step back from the film for a moment and look at the idea underneath it. Because that's the part that outlives any one product. For a century, we solved heat one way: build a machine, feed it, power, force the warmth somewhere else. It worked, and in doing so, quietly became one of the world's largest demands for electricity. What SpaceCool really proves isn't the success of one Japanese company. It's that we've been looking at the problem from the wrong direction. A surface doesn't always need to fight heat. Sometimes it simply needs to let it leave, quietly, continuously, and without electricity. We didn't need to overpower the heat. We needed to stop standing in its way. And that's exactly where this idea matters most. The places warming fastest are often the ones least able to afford round-the-clock air conditioning: crowded cities, hot climates, fragile power grids, and rising energy costs. A cooling layer that asks for no electricity, no upkeep, and no wiring isn't a luxury there. It's a lifeline. Because the people who need cooling the most are so often the ones priced out of it. And this is a way to cool without that price. That's the quiet revolution in material science. Not a machine that fights nature harder, but a material that works with it. Using the sky itself as part of the cooling system. SpaceCool is one early version of that idea. It won't be the last, because the real breakthrough was never just a film on a roof. It was a completely different way of thinking about heat. It was realizing that one of the coldest places in the universe had always been just above our heads, free, silent, and waiting. We just had to learn how to open the window and let the heat out.